We're going to look at factorial ANOVA theory. In a factorial ANOVA, we're looking at two or more independent variables across a single dependent variable. So just like a one-way ANOVA, where we have only one dependent variable, what changes in a factorial ANOVA is that we have two or more independent variables. As a result, these analyses are a bit more complex because we're going to have to calculate more than one ANOVA result. We're going to have to look at an f-test for each independent variable, as well as something called an interaction term. We'll have an f-test for an interaction term. When we look at an f-test for each independent variable, we call those main effects. That's an important term that I want you to keep in your head here, that a main effect is an f-test for one of the independent variables. An interaction effect is how the independent variables are working with the dependent variable together. So you're going to be looking at both the independent variables together across the dependent variable, how these the interplay between each of the independent variables. And I'll illustrate that for you so you can understand that. We're not going to compute a factorial ANOVA by hand in this class, but if you want to know how to do that, you can look at my course notes on pages 21 and 22, and I'll show you how to do that. So we are going to look at, for a factorial ANOVA with two independent variables, we'll look at three null hypotheses, which you see here. A null hypothesis for the first independent variable, for the second independent variable, and then for the interaction term. When we compute an interaction term, we can graph it, and I'm going to show you how we graph an interaction term in SPSS. But first I want you to understand what this looks like. Let's say that we're going to do a factorial ANOVA across depression scores, and we're going to have two independent variables, a gender IV and a socioeconomic status IV. Here we see an example of a non-significant interaction. Notice that the socioeconomic status categories are on the horizontal axis. The male and female, the other independent variable, are separate lines in the graph, and that the test scores on the depression inventory is the y-axis, or the vertical axis. And you can see that what's happening with males is the same thing that's happening with females. For both groups, the low SES group scored the highest. And for both males and females, the high SES group scored the lowest on the depression inventory. So what's going on with males is the same thing going on with females. There's no significant interaction. The pattern of responses is the same. That would not be the case here. Notice here that depression scores for low SES males are the highest, but for females, depression scores were highest for the high SES group. We can't generalize across each of the independent variables now because what's going on for males is very different than what's going on for females. We would need to evaluate males and females separately. So when there's not a statistically significant interaction, we can look at each of the main effects. Same way that we'd interpret a one-way ANOVA, but we do it for each independent variable. However, when we do have a statistically significant interaction, we need to graph the interaction and examine each level of an independent variable across the other independent variable. And that process is known as simple effects. We can't look at the main effects in a significant interaction. We have to look at the simple effects. Now there's two ways that we could evaluate simple effects. The first way we could evaluate simple effects is that we could separate males and females, and we could look at low, middle, and high SES depression scores for males only, and then we could look at low, middle, and high depression scores for females only. So we separate males and females. The other way we could do this is we could separate based on socioeconomic status. So we could look at the differences between males and females in the low group, differences between males and females in the middle group, and differences between males and females in the high SES group. It doesn't really matter which method you use. It will depend more on what you're interested in finding. So if you're more interested in socioeconomic status differences, you might use the first method. If you're more interested in looking at differences between males and females, you might look at the second method. But you probably wouldn't do both. When we do a factorial ANOVA, we're going to start off the same way we did with one-way ANOVA. We're going to analyze model assumptions, but then we have to determine if there's an interaction effect. And depending on if there's an interaction effect, we'll either, for a non-significant interaction, look at main effects, and then we compute our effect size for our main effects, and then we do our post hoc analyses if necessary, and always continue to look at effect size. Or we have a significant interaction, and we plot the interaction, and then we analyze simple effects. And then, of course, we compute effect sizes for each simple effect, and then perform any post hoc analyses that we would need for each simple effect. And I'll illustrate these in the coming lectures.